what I mentioned earlier is that we will start with the arena in which all this takes place, namely space and time. And the reason for that is when you imagine a body symbolized by this point here, let's say this is a mass, and that moves around in space. Then, if I draw it this way, just this way, we cannot really describe this mathematically, because what is the dynamics of the system or the evolution of the system? We describe how the system, the position, the velocity of the system changes in time, how that evolves as a function of time. Now, in order to specify the position, we need a reference frame. We need coordinates, and coordinates require a reference frame. So it makes a difference if I have, say, a coordinate system here, and then I describe the position of that body in that coordinate system, or whether I shift the coordinate system here, and then I will have different coordinates of the same body. So, strictly speaking, what we describe in mechanics is always the evolution of a system, of a mechanical system, with respect to some reference frame. And so, the first thing we have to do before we start doing mechanics is we have to specify and we have to agree on a reference frame. Now, a reference frame, let me shift it back to the original position. A reference frame consists of spatial coordinates, so that's what I drew here, x, y, z axis. And in addition, it consists of a clock, because as I said, describing the evolution in time means we need a notion of time. So we have to say at which time the body is where, and in order to do that we need a clock and we need a coordinate system in space. Now let's suppose we have a clock, and this clock tells us time t, and we have this coordinate system that I just drew, and this coordinate system here I drew a Cartesian coordinate system is spanned by basis vectors. So let me try to indicate these basis vectors. We have Ex, Ey, and Ez. So these are the basis vectors pointing in the direction of the x, y, and z axis. And now we can say we describe the motion of this body with respect to this reference frame. So we have a vector, a position vector, r of t, and the position vector r is the vector connecting the origin of my reference frame with the body that I want to describe, and that vector evolves as a function of my clock time t. In this reference frame I have components, so I can write this vector here in components, and the way I do that is I say I have coordinates x, y of t, e, I. Maybe I should have written sorry, I just realized that rather than x, y, z, I should better have used 1, 2, 3. That suits me a little bit better. 1, 2, 3. Because I would like to denote the position vector by x of t. Then I goes from 1 to 3. And I write this in this way. Now imagine, that's all fine so far, but now imagine somebody else decides that it's more suitable to describe the system in a different reference frame. So a colleague of yours might say, you chose a bad coordinate system. I think this one is much better. And also your clock doesn't do any good. I prefer a different clock. So that's a clock prime that shows a time t prime. And your colleague's coordinate system now has basis vectors e1 prime, e2 prime, and e3 prime. And then, of course, for your colleague, the motion looks perhaps totally different, because your colleague observes how the coordinates of the body change in time, and since he has or she has a totally different reference frame and different clock, the motion can look totally different in principle. Now let's think about how, so if the observations of one observer can be translated into the measurements or the observations of the other. So how we can transform from one reference frame to the other. Now, first of all, we should notice that the spatial reference frame of your colleague differs from your own reference frame in two respects. One respect is that it may have a different origin. So the origin of the second reference frame is shifted with respect to the origin of your first reference frame by a vector d, a distance vector d, and this may actually depend on time. Think about two scientists who perform experiments. One is standing on the platform of a train station, and the other one is riding on the train. And so the first one will have a reference frame that is sort of at rest on the platform, and the other colleague will measure positions with respect to the train, but the train is moving. And therefore, the origin of the second reference frame is moving with respect to the origin of the platform reference frame. So this is one difference. The other difference is that the basis vectors ei primed, they can be rotated with respect to the ei's. So you can have, let me denote these differences. So this is one difference. A second difference is that the ei prime is in general rotated with respect to the ei, and I denote this with a rotation operator. And in general, this rotation operator may also depend on time. There's a very simple example. We are here in this lecture hall, and if we do an experiment here in this lecture hall, then we would obviously use as a reference frame, we would use a coordinate system that is at rest in this lecture room. But somebody who is out in space and watching the Earth from a spaceship uses the frame of the spaceship. Now the Earth is rotating, so in fact our reference frame that we use in this lecture room is rotating with respect to a reference frame in a spacecraft. And therefore, our basis vectors here are rotated against the basis vectors of the spacecraft, and this rotation is time dependent. And then there's a third possible difference. As I mentioned, your colleague might also use a different clock. So it may also be the case, and this is here number 3, that actually the time is different. So t prime is not equal to t, but is shifted with respect to my time by some s, some time interval s. Okay, so this is the most general setting, and next I would like to understand, together with you, how we can translate motion in one frame to motion in the other frame. Now, to do that, I would like to, this is a somewhat tricky drawing lesson, but I'd like to draw the picture that I had on the previous page in a slightly different way. And namely not in space, but in space-time. Now, let me suppress one of the 3 dimensions, otherwise I can't draw it. And let's say I have only 2 spatial dimensions, namely x and y, with basis vectors ex and ey. And now let me add as a 3rd dimension, let me add time. So the vertical axis is a timeline. Let me draw this perhaps in green. Not so easy. Okay. Now, and in my clock, here is time equal to 0. And then I have somewhere here, let's say I have time s, and further up I have time t. So you see that approximately how the clock is ticking as I go upwards. I try to indicate here a 2-dimensional plane. So this plane indicates, I should say, now a point in this space-time diagram is now no longer a point in three-dimensional space, but it's an event. So a point in this diagram tells you where it happens and when it happens. And a horizontal plane, as I just drew, are all the events that in my reference frame happen at the same time. Okay? So these are all the events that happen at time 0. And then let me try to indicate here all the events that happen at time s. And then finally, it's so easy, all the events that happen at time t. Now, what does the second observer look like in this diagram? The origin is shifted with respect to my origin. And also the time is shifted with respect to my time. Actually, this, what I drew here in green, this is called a world line. This is the world line of the observer. Okay. Now my colleague, say the one traveling on the train, my colleague has a different world line. And his or her world line will in general look like this. So this is the world line of observer prime. We said that the clock of the second observer runs differently from my clock. And therefore, when my clock shows S, the clock of my colleague shows 0. So here, when the second observer crosses this plane, then his or her clock will actually show 0. And when my colleague's is at my time t, then my colleague has time t prime, which we said is t minus s. So here we have incorporated the fact that clocks run differently. Now, at time t, my reference frame in space, my coordinate system in space, still looks like this. So at time t, here's the origin of my spatial coordinate system, Ex and Ey. My colleague's coordinate system is, first of all, the origin is displaced. So my colleague will have the origin of his or her coordinate system here. And we said that they differ by this distance vector d of t. Okay. So at time t, my time t, my colleague's spatial reference frame has an origin which is displaced by this distance vector d of t. And my colleague then has basis vectors which are rotated against mine. So they might, for example, they might be oriented like this. So E 1 primed and E2 primed. Just caught myself. I should again call it E1 and E2. Sorry. Doesn't make a big difference, just for consistency. So we have here E1, E2, E1, E2. So this is the world line of my colleague, and his or her basis and clock, and then last thing, and then we have a little break. What do we want to do, my colleague and I? We want to describe the motion of a mechanical body. So there will be the world line of our body here, and this may be sort of an interesting motion. This is the world line of our body. Okay, now we both describe, both want to describe the motion of that body, both my colleague and I. I do that with this position vector here, so x of t, and my colleague does it with a position vector x prime of t, which is relative to the origin of his or her spatial coordinate system. On the previous page, I had given a formula how time and the new reference frame are related to the original time and reference frame. And as for the time, the relationship was t prime is equal to t minus s. And one of you asked the question, which is a very good question, is this really the most general way in which the new time is related to the old time? And in fact it is not, because if I use time t, then somebody else might use t prime, which is given by the cubic root of t, for example. That is, maybe with the exception of t equal to 0, but otherwise it's a strictly monotonic function of t. So there's a one-to-one mapping between t and t prime. And that's a perfectly fine definition. It makes the equation of motion terribly complicated, but in principle there's no reason why I shouldn't have sort of more general clocks that differ from my clock not just by a shift, but it's just an arbitrary function of my time. So in principle this is possible, but in a minute I would like to explain to you why I would like to focus just on these time shifts. Another question which is similar, sort of in spirit, is when you look at the relationship between the new basis vectors and the old basis vectors. I said the new ones are related to the old ones by a rotation. Now rotation is represented by an orthogonal matrix, and an orthogonal matrix preserves lengths and angles. So if my original frame is an orthonormal frame, so these are the EIs are unit vectors, and they are orthogonal, then the new basis will also be an orthonormal basis. And there again was the question, is this really the most general way we can do that? And again, the answer is no. You could also envision more general transformations where the new reference frame is no longer orthonormal. But there are reasons, and I hope they will convince you why we should limit ourselves to these forms of the transformation. And in order to explain that, I would like to go back to this picture here. I would like to agree with my colleague that at least we should see the same space-time structure. What does that mean? First of all, it means that I would like to preserve the notion of simultaneity, so that when I see two events in my reference frame which happen at the same time, they're simultaneous, then I would like to make sure that my colleague who uses different reference frame at least also sees these two events as simultaneous. So in other words, I indicated these two-dimensional planes. They contain events that for me are simultaneous. And I want to make sure that for my colleague who moves on the different world line, these events are also simultaneous. Now, this is guaranteed as long as the modified time t prime is a function of my time t only, and is not a function of space. Because otherwise, if I have two events that are simultaneous for me, but at different locations in space, and now the transformation of clock time is space dependent, then this would mean that for my colleague, suddenly these events also have different types, and they are no longer simultaneous. So, this implies that t prime must be a function of t only, and not of position. I mean, perhaps this all looks very obvious to you, and you may wonder why we spend so much time on this. But already at this point, when you study special relativity, you will see this is no longer true. So already this very first requirement distinguishes non-relativistic mechanics from relativistic mechanics. Now, the second requirement is that I would like that we see, perhaps we don't have the same clock time, but at least we have the same notion of duration, of length of time. So I would like to make sure that we preserve time intervals. Now this, of course, immediately singles out this transformation law that I had written on the previous page, just an additive constant, and then we see the same time differences between two events. And the third requirement is that also, when I look at simultaneous events, then I can define a spatial distance between the two. And I want to require that the two observers see the same spatial distance. Yeah? So I want to preserve spatial distance of simultaneous events. Now, attention, it's important to say, to limit that to simultaneous events. Because if we have two events at different times, then again, each observer can calculate the spatial distance between these events, but they don't have to be equal. Now, this implies, well, how is spatial distance measured? For an observer, I take the position vector x of t, so in my reference frame. In my coordinate system, this vector x of t has components xi from 1 to 3. And then I can, if I have two events, I can look at the difference of these coordinates and then simply the sum of the squares of the delta x's. Square root of that gives me the spatial distance between the events. And my colleague does the same. And to make sure that we obtain the same distance in our respective coordinate systems, this implies that indeed the basis vector of my colleague can only differ from my basis vector by an orthogonal transformation, so a rotation operation, which may depend on time, where R is orthogonal. Let's now look at how the components, or the components of position, velocity, and acceleration change when we go from one reference frame to the other. Now, in the original frame F, the body has position vector x, and in my coordinate system with basis vectors ei, this implies that I measure, that I observe coordinates xi. What's the velocity that I see? The velocity in my frame, that's x dot, and this is sum over I xi dot ei. And I'm assuming here that my frame is not time dependent. So my frame is fixed, doesn't change in time. So all that changes in time when I describe the body are the coordinates of that body. And then finally I have the acceleration a. This is the second order derivative of position, and this is sum over I xi double dot ei. Now let's go to the frame of my colleague. This colleague has frame f prime. There's a distance vector x prime which is related to, there's a position vector x prime which is related to my position vector x by this shift d. Also, my colleague will describe this position vector x prime in his or her rotated coordinate system. So we'll describe, my colleague has a basis vectors ei prime, and in this basis, now this position vector has components xi primed. Now what's the velocity vector that my colleague sees? V primed. This is by definition, this is how velocity for my colleague is defined. This is again expressed in the reference frame of my colleague, so ei primed, and the components of the velocity that my colleague sees is simply the time derivative of the primed components. Yeah? And likewise, the velocity, the acceleration that my colleague sees is again expressed in the basis of my colleague, and then I have the second order derivative of the coordinates that my colleague sees and measures. So what we would like to do now is to relate. I mean, we've already related the position vectors to each other, x and x prime, and now we would like to relate the velocities and the accelerations to each other. I claim that v prime, as defined there, I can also write that as d over dt sum over I xi ei xi primed ei primed. But then by product rule, when I do that, then I get a contribution xi prime dot ei primed. That's what I wrote as the definition. But then I also get, since the basis of my colleague is rotated against my basis, and this rotation may be time dependent, the basis vectors ei prime may be time dependent. So I have to compensate for that by subtracting xi prime ei prime dot. This here, this is x prime. So we have this equals x prime dot minus sum over I xi prime ei prime dot. Now, we know x prime is related to x by this shift d. So x prime dot is equal x dot minus d dot. So this is equal x dot minus d dot minus sum over I xi prime ei prime dot. And this in turn here is by definition equal to the velocity in my frame. Right? So we get a transformation law that says the velocity that my colleague sees is equal to my velocity minus d dot. So that's the velocity of the distance vector between the two of us. Minus sum over I xi prime ei prime dot. Let's look at the acceleration. Let's look at the acceleration. So we have a prime. Now we could say this is simply this is v prime dot. Now, but when we take the time derivative of v prime, look at the definition of v prime, we have the same problem here. By product rule, we get a second order derivative of the coordinates xi prime. That's what we want. But then possibly the basis of my colleague is time dependent, and therefore we get also a time dependent basis vector. And we have to subtract that. So we have minus sum over I xi prime dot ei prime dot. We can now insert this result here, sort of the previous result in here. We know v prime dot. For v prime, we use the previous result. So we get v dot, so we get v dot minus d double dot minus, and then from that we get two contributions by product rule, we get first a contribution xi prime dot ei prime dot, which is the same that we already have there. So we get, in total, we get this twice. We have minus 2 times sum over I xi prime dot ei prime dot. And then finally we get a contribution sum over I xi prime ei prime double dot. Now this here by definition is my acceleration, that's the acceleration that I see. And therefore, taken together, we can say the acceleration that my colleague sees is equal to the acceleration that I see minus the second order derivative of the distance vector between our reference frames, minus 2 times sum over I xi prime dot ei prime dot minus sum over I xi prime ei prime double dot. Now this here, this correction, this is how the acceleration that my colleague sees differs from my acceleration, and this term here is sometimes called the fictitious acceleration. So my colleague sees an acceleration that differs from the acceleration that I see by so-called fictitious acceleration, and this fictitious acceleration is not due to a physical force, but is entirely due to the fact that my colleague moves in a different reference frame. I would like to make it a little bit more concrete in the last 10 minutes with 2 simple examples. The first example is a linearly accelerated frame. Imagine you have, as we have here on Earth, you have a uniform gravitational field with gravitational acceleration g. Now imagine that you have a mass freely falling in this gravitational field. Now I am on the ground waiting for the arrival of this mass. So I am here watching, and my reference frame is here. Okay? This is the E1, E2, E3. Okay? Now my colleague, let's say that, let's say that here is a high-story house, right? High building. And my colleague, a very brave fellow, has jumped off this building, okay, and is now also freely falling and watching the mass. Okay, and hopefully, just before hitting the ground, he will pull the parachute and land safely. But for the time being, my colleague is freely falling, and my colleague has a reference frame here, E1 prime, E2 prime, E3 prime. Now our reference frames, they have the same orientation, so in that respect it's trivial, but they have different origins, right? So we are separated by a distance vector d of t. Now, what is the acceleration that I see of the mass? The acceleration that I see is g. Okay. The acceleration that my colleague sees, A prime, is, according to the general formula that we had on the previous page, let's look at these terms one by one. So my colleague sees A, which is g, minus d double dot. This is non-zero, right? And it's also g, because if my colleague falls with the same acceleration as the mass, then it's also g. Now, and then we have two terms that contain time derivatives of the basis vectors. But I said the basis vectors, they have the same orientation. So in this simple example, these derivatives vanish. They are zero. And so the only term that contributes is this d double dot. So let me just write this formula as A minus d double dot, which is g minus g, which is equal to 0. So as expected, that's of course a trivial example, my colleague sees acceleration 0 of the mass. Let's come in the last few minutes to a less trivial example, and that is a rotating frame. This is my frame, which is fixed, and now my colleague sits, for example, sits on a carousel and is rotating around an axis. Let's say the rotation axis is this axis here, and there's a rotation with angular velocity v, omega, right? And now my colleague has a different frame, the red frame, and since my colleague is rotating around the origin, these basis vectors are rotating with respect to my basis vectors. So what do we have in this case? We both have the same origin for our frames. So the distance vector d is 0. But the basis vector ei rotates with angular velocity, so ei prime rotates with angular velocity omega around the origin. And this means that we look at the change in time of basis vectors, vector ei prime. This is given by angular velocity omega vector product with ei prime. More generally, when a body with position vector r rotates with angular velocity omega around an axis, then the velocity v of that point, so v, which is equal to r dot, is given by omega cross r. Have you seen that before in your mechanics class? Yeah? So that this general formula applies to the rotating frame, to the basis vectors EI prime.